Okay, so welcome to this video. In this video what we're going to do is discuss the P2X receptors, which are a type of ligand-gated ion channel. Okay, so the structure for this video then, I'm going to start off with a basic discussion of the different types of ligand-gated ion channels. Okay, because all ligand-gated ion channels can be classified into one of three families. At least all known ligand-gated ion channels, at least in the human, can be categorized into one of these three families. Okay, so we're going to start off with those three families, and then we'll look specifically at the P2X receptors, and there's multiple P2X receptors, so we'll look at the different types. Okay, right, so some of the stuff that I am going to give you in this video is not yet standard enough to be put in textbooks, and therefore I'm going to start off with a little reference, which is where I got all of my information from for making this video. So most of the information comes from this reference, Alan North, who wrote a review about the P2X receptors in 2002. Okay, so if you Google that, you should be able to get up the review and you can check that I'm giving you the information correctly. So the first classification that we're going to discuss about the classification of ligand-gated ion channels into three families, that's not from this review, that's standard textbook stuff, but the P2X receptor stuff that we're going to come on to is then less standard, and it's not yet fully covered in textbooks, so you have to go to the secondary research literature. Right. Okay, so what we're going to start off with then is the categorization of ligand-gated ion channels into these three different families. So, firstly, what is a ligand-gated ion channel? Well, basically the name tells you exactly what it is. It is an ion channel, i.e. a channel which conducts some sort of ion, maybe a sodium ion, maybe a potassium ion, a chloride anion, a calcium cation, an ion of some sort. And usually it is closed. However, when certain ligands bind to it, so just molecules, okay, they will cause it to open. So these are ion channels that we can make open by binding certain chemicals or ligands onto them. Okay, and ligand-gated ion channels are usually abbreviated to, not like that, slash that. Okay, they're usually abbreviated to L for ligand, G for gated, I for ion, and then C for channel, so LGIC. Right, okay, so let's now discuss the categorization of ligand-gated ion channels into three families. So the first family is named after the P2X receptors, so they are the main members of this family. So this family is called the P2X-like receptors. Okay, so all of the receptors which are in this family of P2X-like receptors, they all have a conserved structure which is similar to the P2X receptors. And I should just stress, there is not just one P2X receptor. So the P2X receptors itself is an enormous great family of different receptors that are all categorized together. This is a bigger family. This contains more families of receptors than just the P2X receptors. Okay, so what's the structural feature that you have to be considered a P2X-like receptor? Well, basically, what these P2X-like receptors all have in common is that they are trimers. Okay, so if I draw a picture of this, let's say this is our ligand-gated ion channel here, and I'll draw a pore down the middle, which is where the ion will be conducted. Okay, and basically these P2X-like receptors, all of them are made up from three proteins stuck together to make a P2X-like receptor. So they are trimers, that's the starting point. Okay, in addition, they are, if we look at the structure of one of these subunits of a P2X-like receptor, it has conserved features. Okay, so let me say, let's pull out one of these subunits of a P2X-like receptor and have a look at its membrane spanning topology. Okay, right. So, if I draw the membrane again here, let this be the extracellular fluid side of the membrane, so ECF for extracellular fluid, and let this be the cytoplasmic side of the membrane over here. Okay, basically, these P2X-like receptor protein subunits have this conserved structure. So, their amino terminus is always on the cytoplasmic side, like so. Then they have a membrane-spanning alpha helix, which will have a huge number of hydrophobic residues within, which will straddle the membrane. Okay? They will then have an extracellular loop, and they'll then have a second membrane-spanning alpha helix, which will straddle the membrane again, and then they'll arrive back within the cytoplasm. So this line, this is representing a polymer of amino acids. It's representing a polypeptide. So it's amino acid after amino acid after amino acid after amino acid. And this is the membrane-spanning topology, as it's called. So you're telling us where there are membrane-spanning alpha helices, basically. Okay, so basically this is the structure of one of these subunits here. Okay, so we've pulled out one of these and it looks like this. So to make a P2X-like receptor, you need to have subunits which have this membrane-spanning topology. You need to stick 3 of them together, and that will make you the whole ion channel, basically. That is all you really need to have to be considered a P2X-like receptor. So these are the characteristic features that put you into this family. Okay, right. So the main example of receptors which are all put in this family are the P2X receptors, but there are other examples as well. Okay, so we will come back and discuss these more in a moment. Okay, but let's continue on with the different families of ligand-gated ion channels. So this is the first family of ligand-gated ion channels. You have ligand-gated ion channels which are trimers and which are made up of 3 protein subunits which have this characteristic membrane-spanning topology over here. Okay, so now let's move on to family 2. Okay, so family 2 of ligand-gated ion channels are the glutamate-like receptors. Okay, and these are receptors which have a very similar structure to the main glutamate receptors. Okay, so I'll show you the structure that you have to have in order to be put in this glutamate-like receptor family. So, just as the P2X-like receptor family was named after its major example, which is the P2X receptors, the glutamate-like receptors are named after, this family is named after its main member, which is the glutamate receptors. Okay, at least the ionotropic glutamate receptors. There are, after all, also metabotropic glutamate receptors, which we're not interested in here, because they're not ligand-gated ion channels. Right, okay, and I should have said that actually. Another word that people often use for ligand-gated ion channels is ionotropic receptors. That's a bit of terminology that is common among neuroscientists. You'd never catch a pharmacologist calling ligand-gated ion channels ionotropic receptors, but neuroscientists love this word. They love their ionotropic and metabotropic distinctions. Okay, right, so glutamate-like receptors. So here we have our glutamate-like receptor, our ligand-gated ion channel. Okay, and it's sitting within the plasma membrane here. Okay, and once again we've got the pore through which the ions will actually move, and this time these receptors are tetramers. They're made up of 4 separate proteins all stuck together. Okay, so this is a tetramer. Okay, now, same protocol. What we'll do is we'll take one of these protein subunits out now. We'll pull this out and have a look at its structure. Okay, and we want to see what's its membrane-spanning topology. So, let's have our plasma membrane here, and basically we're now looking just at a single one of these subunits which makes up a glutamate-like receptor. Okay, so the membrane-spanning topology then, their conserved structure is that they have the amino terminus extracellularly, so here's the amino terminus on the extracellular fluid side. Then they have their first membrane-spanning alpha helix here, which is known as M1. Okay, so this is called the first membrane-spanning alpha helix. Then they have a re-entrant loop, which basically means you sort of try to go across the membrane and then you fail and come back. So this is called a re-entrant loop. Now, the re-entrant loop is so important that it is actually given its own name. It's called M2. So the re-entrant loop, the entire thing from here all the way down to here, that's all considered M2 of the glutamate-like receptor. Then you have M3 and then M4, so 2 more full membrane-spanning alpha helices. This third membrane-spanning alpha helix, well actually it's only the second, but it's called M3. Okay, and this one here is called M4, which then leaves the carboxylic acid terminus of this subunit on the cytoplasmic side. So that's the conserved membrane-spanning topology of the subunits of receptors which are glutamate-like receptors. Okay. Now, another interesting fact that is conserved among all these glutamate-like receptors is that the ligand binding domain is made by a portion of the polypeptide that is prior to the first membrane-spanning alpha helix, and it's also made up of a portion that is within this M3-M4 loop here. So those two portions that I've shown in red here, what's going to happen is those are going to stick together, and then that will make the ligand binding domain, basically. That's where the ligand will bind, so where, for instance, glutamate will bind if we're talking about a glutamate receptor. Okay, so basically to be a glutamate-like receptor, you have to have this sort of a membrane-spanning topology with this structure where the ligand binding domain is made by a portion prior to M1 and also a portion within the M3-M4 loop, dimerizing together. And you also need to have this tetrameric structure here, so you have to stick 4 of those together to get the whole ligand-gated ion channel. Okay, and the key examples here are the glutamate receptors. Okay, so for instance the AMPA glutamate receptors, which again is not just one receptor, but there's a whole family of AMPA receptors, and they are all within this superfamily of glutamate-like receptors. Then there is the NMDA family of glutamate receptors, and again that's a whole family. There are loads of NMDA receptors, and then the whole family of NMDA receptors is within this superfamily of glutamate-like receptor. Okay, and then finally another form of glutamate receptor, the kainate receptors, which are again a whole family. There's many kainate receptors. All of those then are in this superfamily of glutamate-like receptors. Okay, so glutamate is the most important excitatory neurotransmitter within the brain. Okay, so these are the receptors that mediate that. Okay, mainly the AMPA and the kainate. NMDA is thought to be very important in long-term potentiation. Right, so that's the glutamate-like receptor family. Now the third family is probably the most studied of all the families of ligand-gated ion channels. Okay, and a lot of your old favourites you'll find are in this family. Okay, so this is the nicotine-like receptors. Okay, but it's got a more famous name. This is the name that people are trying to have this family renamed as, but it's got an old name basically, and its old name is more commonly used. Okay, so its old name is to call these things cis-loop ligand-gated ion channels. So this other family is called the cis-loop ligand-gated ion channel family, and I'll just abbreviate ligand-gated ion channel to LGIC. Okay, so this is the cis-loop ligand-gated ion channel family. Okay, right, and sometimes they're just called cis-loop receptors, and that's because they have this structure called a cis-loop within their subunit structure, and I'll discuss that in a moment when we get to the looking at the structure of a single subunit. So let me start off with what the actual receptor is built out of. So basically, all nicotine-like receptors are pentamers. So we've gone from trimers up to tetramers, and finally we're going to pentamers. Okay, so here is the ion pore that moves through the membrane and will conduct sodium, potassium, chloride, calcium ions potentially through there. Okay, and it won't conduct all of them necessarily, or have its preferences. Okay, and that will vary depending on exactly which receptor you're talking about. Okay, right. So these are made up of 5 separate subunits, 1, 2, 3, 4, 5, all sitting next to each other like so. Okay, so 5 of them will cluster up to make the whole channel. So now, same protocol, let's pull out a single one of these proteins, the one that I'm highlighting in pink here, and let's have a look at its membrane-spanning topology. Okay, so again, here's our membrane. This is the extracellular fluid side here, and this is the cytoplasmic side. And basically, for the subunits of nicotine-like receptors, you have the amino terminus extracellularly. Then you have, in the extracellular domain, a special structure called a cis loop. Okay, so this is called a cis loop, and this is conserved among the subunits of whatever cis loop ligand-gated ion channel you're actually talking about. Okay, so that's always conserved there. Then you have your first membrane spanning alpha helix called M1. Okay, so this will be called M1. Then it continues on. You've got your second membrane spanning alpha helix, M2. Third membrane spanning alpha helix, M3. You have a very large loop between M3 and then M4, which is called the intracellular loop. Okay, so this little loop that we've got here is called the intracellular loop, which dangles down into the cytoplasm. And then finally you end with the carboxylic acid terminus extracellularly. Okay, so this is the M4 membrane spanning alpha helix here. So it's M1, M2, M3, M4. Right, so that's the subunit composition of a subunit of a ligand-gated ion channel that is within this nicotine-like receptor family of ligand-gated ion channels. Okay, right, let me now just discuss with you what a cis loop actually is. So basically, this is a loop in the polypeptide structure that is held together by a disulfide bond between two cysteine residues. So let me try and show this here. Okay, so what you'll have is this line will represent a polymer of amino acids. So it's amino acid after amino acid after amino acid after amino acid, and then suddenly I'm going to actually draw the amino acid structure out. And this is because this is our cysteine amino acid, which is going to be involved in the disulfide bond that will hold this loop together. Okay, so the R group of this cysteine amino acid is going to be a methylene group, then with a thiol group. Now, a thiol group would normally have a sulfur atom and then a hydrogen atom. Okay, but I'm going to be fortuitous because I want this cysteine residue that I've drawn here to be involved in a disulfide bond with another cysteine residue that's on the other side. Okay, which means it's going to lose its hydrogen, so I don't want to draw its hydrogen. Now I'm going to go back to representing the amino acids polymerized together just as a line. So this line is representing amino acid after amino acid after amino acid after amino acid. Okay, then you have the amino terminus of our next cysteine on the other side of the loop now. Here is the alpha carbon with a hydrogen coming off. Here is the R group of this cysteine amino acid, which again will be a methylene group with a thiol group coming off it. And now both of these sulfur atoms have lost their hydrogen atoms, and they'll then bind to one another like so. Okay, to create that special bond there, which is called a disulfide bond. So this bond between those two sulfur atoms, that's called a disulfide bond, also sometimes called a disulfide bridge. Okay, right, and that's a very, very strong bond. That, you know, that's the one that's difficult to break when you're doing like a Western blot. You have to add on a special reducing agent to break it, generally dithiophenol or beta-mercaptoethanol. Okay, heating up proteins breaks generally all of the bonds apart from those. Okay, so that's a strong, strong bond there. Right, so this structure then, which is a loop in the polypeptide structure, is called a cis loop because cis is the three-letter amino acid code for cysteine, and cysteine amino acids are the amino acids which hold this structure together. So this is a cysteine amino acid, this is a cysteine amino acid. Okay, so that's why it's called a cis loop. So all of these cis loop ligand-gated ion channel family subunits all have one of these cis loops within their extracellular domain. Okay, so this is a massive great superfamily once again, and within this there are some very, very famous families of ligand-gated ion channels. Okay, so let me give you some examples of cis loop ligand-gated ion channels. So the nicotinic acetylcholine receptor family. And again, this is not just one receptor, there are a huge number of different nicotinic acetylcholine receptors. So I suppose I should write this name out in full. So the little N there is for nicotinic, the ACH is for acetyl, that's the A, and then the CH is for choline, and then the R is for receptor. Okay, so there isn't just one nicotinic acetylcholine receptor, so I should put receptors. Okay, so this is a massive great family of receptors which are all very, very similar and which respond to acetylcholine as well as, in some cases but not all cases, nicotine. Okay, so not all of the members of the nicotinic acetylcholine receptor family actually do respond to nicotine, which is a good thing because you have nicotinic acetylcholine receptors all over your skeletal muscle, and if those responded to nicotine, then nicotine would be what would cause contraction of the muscle, and it would cause uncontrollable convulsions, basically. So it's a good thing that nicotine does not stimulate all nicotinic acetylcholine receptors. Nevertheless, the entire family is named after the fact that nicotine stimulates them. Okay, right, or at least some members of that family. So this huge great family of receptors is just a subfamily of this even bigger family of receptors. Okay, so another great big family of receptors which is within this larger superfamily is the GABA A receptors. Okay, so again, this isn't just one receptor, there are a huge number of different GABA A receptors. Okay, now, just as I said, glutamate was the most important excitatory neurotransmitter within the brain, GABA, for gamma-aminobutyric acid, is the most important inhibitory neurotransmitter in the brain. Okay, so these GABA A receptors, when GABA binds to them, they open and they allow chloride anions to move from the extracellular fluid into the cytoplasm to hyperpolarize the electrical potential difference across the cell membrane, and hence make it less likely that a neuron will fire an action potential. Okay, right, so this great, massive, important family of receptors is just a subfamily within this bigger superfamily of receptors. Okay, another important example, you also have the 5-HT3 receptors, and again, there isn't just one 5-HT3 receptor, it's a family of receptors. Okay, so there are a huge number of serotonin receptors, and the other name for serotonin is 5-HT for 5-hydroxytryptamine. Okay, most of them are G protein coupled receptors, nothing to do with ligand-gated ion channels, but the 5-HT3 receptor family are ligand-gated ion channels, and they are all within this family of nicotine-like receptors, or cis-loop ligand-gated ion channels. Okay, and then a final family that's within here are the glycine receptors. Okay, so the GlyRs. So again, this isn't just one receptor, it's a family of receptors, and all of them have the same pentameric structure with this same basic membrane-spanning topology, and therefore are put in this superfamily of nicotine-like ligand-gated ion channels. Okay, right, so we'll call it there for this video. That now concludes our discussion of the basic categorization of ligand-gated ion channels into these three separate families. In the next video, what we'll do is an in-detailed study of the P2X ligand-gated ion channels.